This is a combination lesson that's going to look at both 6 and 7, which is on confidence intervals and hypothesis tests for averages. We've already looked at how to do confidence intervals and hypothesis tests for one proportion and for two proportions. This is going to look at how I can go from a sample average X bar to how I can make predictions about a population mu, and also how to test claims about population mu. Something to keep in mind is the central limit theorem from earlier stats courses. This says that X bar follows a normal distribution with just labeling things, a center of mu, and a standard deviation of sigma over the square root of n. So just a reminder, sigma is a population standard deviation, S is a sample standard deviation. So what this is telling me is that my sample average should be close to my population average. Intuitively, that kind of makes sense. So if I did the sample weight of 600 bagels at a store, that should be reasonably close to the population average weight. There are three assumptions for using this. Random, this means I'm collecting that data without bias. If I was only taking the small bagels, that wouldn't work out. Independent, I need to make sure that the weight of one does not affect another. The backup for that is sampling less than 10% of the population. Sampling less than 10% of the population means that things are kind of spread out in such a way that they don't affect each other. And finally, large N. Large N means N is greater than or equal to 30, or the starting distribution looks like a normal graph. And normal is sort of this bell shape. So if I graphed the data and it looks something kind of like this, I'd be like, oh great, that's starting kind of normal. Where if I had something that started out like this, I'd be like, yeesh, that is not a normal graph. That's too skewed to be considered that bell curve shape. In general, when I'm working with confidence intervals, it looks like center plus or minus whatever distribution I'm working with, critical values for that distribution, multiplied by my standard deviation, but based off of a sample, we call that standard error. Now, you may have used a calculator before to calculate averages and standard deviations. I have my calculator here. It's giving me a sample average for some data that I just typed in, some random numbers of 12.333. And you'll notice it doesn't even give me a symbol for mu. That's because X bar and mu are remarkably close to one another. It also gives me a value for S, my sample standard deviation, 11.7 or so. And it gives me a value for sigma, my population standard deviation, of 9.5 or so. So something that I find a little bit interesting is that in general, your population average looks like your sample average, but your sample standard deviation is a very different number than your population standard deviation. 11.7 is not the same thing as 9.5. So I'm going to keep that in mind when I do this next step. This seems like kind of a completely unrelated aside, but hang on, I'm getting back. So I'm going to take this distribution above, and I'm going to drop it down into my setup for my confidence interval. So my confidence interval for mu is going to be mu, well, that's my center. And I want to say the sample version of it. Well, the sample version of mu is X bar. This is pretty much saying that if I know a large enough sample average, I can reasonably guess what that population average should be. I'm working with the normal distribution, so I'm using z-scores. And I want to take this standard deviation, this sigma over the square root of n, but I want to make it based off of the sample. So instead of sigma, I'm going to put down s. And this is fine in theory because mu and x bar, no problem switching those. I'm using the normal distribution, but here's where I run into a little bit of an issue. I can't just take the sigma and replace it with an s. I actually end up with a considerable amount of error if I do so. So I'm stuck still using this value of sigma. Here's the downside of this. If I know the population standard deviation sigma, I can use this z-score setup that I have here to calculate a confidence interval for an average. But if I knew the population standard deviation, then I probably know the population average too. It's very, very rare that I know both, don't know both things. So the issue becomes, well, what if I just know S and I don't know sigma? And the answer to that is, if I know S, I use something called t-scores. There's a mathematician that was working at the Guinness Brewing Company, and he noticed that when he was using this formula above, he was ending up with a considerable amount of error for small samples. He invented an entirely new distribution that kind of has a built-in error check to it. So my formula is going to look like x bar plus or minus, I'm going to be using t-scores, s over the square root of n. So I have a new distribution, and it's going to work a lot like the normal distribution, but it's going to correct any mistakes that I might make along the way. I like that. So let's see exactly this thing in detail. So the student t distribution, if I wanted to rewrite the central limit theorem, this allows me to switch. This used to be a sigma, I'm writing in an S, and now I can use t-scores. So if I know S, I can use t-scores. If I know sigma, I use z-scores. So here's that formula I had from the previous page, just changing this to a t. My assumption should look pretty familiar. Random, by that I mean no bias. Independent, one sample does not affect another. That's hard to gauge sometimes, so the backup for this is a 10% rule. And the last assumption is a large sample size n. Again, this is n greater than or equal to 30, or it starts normal. We already know how to find x bar and s. That's my sample average and sample standard deviation. And if I don't know how to do it by hand, I can always use a calculator technology to do that. The new part to this, though, is this t star. So let's try to figure out exactly what's going on. And one thing I'm noticing, it says df there. Let's start there. df stands for degree of freedom. This is the number of categories, or the number of items I need to know everything. So suppose I have a coin that I'm flipping, and it could be either heads or tails. And let's suppose I flip 50 times. So I'm working with n equals 2 categories, and I'm wondering what the degree of freedom is. It could be 25-25, but it doesn't have to be perfect 50-50. So let's suppose I flip a coin and I get 23 heads. I needed to know at least this category to get started. Now with this, I'm wondering, does that fix everything else for me? Well, if I have 23 heads, the remainder, 27, must be the number of tails. So by knowing one of these two categories, I was able to solve for the missing one. Let's look at another example. So stoplight, red, yellow, or green. And suppose that I run into this light 50 times in a week. I don't know for sure how many red, yellows, or green just yet. So I'm going to start filling in categories until I can solve for all the remaining ones. So I'm going to put in a 20 there for 20 red lights. I have 30 remaining things, but I don't know what the split is. Maybe it's 0-30, maybe it's 15-15. So I'm going to give you another number. Suppose this is 10. I'm up to 30 so far, 30 out of 50. This tells me my missing category must be 20. So in order to know all three categories, I had to start out with at least 2 of them. And I think you might be seeing what the pattern is. So if I wanted 11 things in a list, and I'm not going to list out 11 things, that would take too long, I would need to know all of them except for that last category which I could solve for. So if I wanted 11 things in total, I would need to know 10 of them. So in general, my degree of freedom is going to be the total number of values here, take away 1. Let's look at an example of this on the next page. But again, degree of freedom is n minus 1. I'm going to show you how to use this t-distribution in just a second. But I wanted to determine the degree of freedom for a quick problem with you before going through anything else on this page. 16 samples. The degree of freedom is the number of categories, take away 1. 16 minus 1 gives me a degree of freedom of 15 here. Well, why does that matter? Well, every single degree of freedom actually creates a different t-distribution because it corrects the error based off of the various sample sizes that we could be working with. This is shown below. So this dotted line that I have right here is a graph that has a degree of freedom of 1 for a t-distribution. The solid line is a graph where I have a degree of freedom of 12. And if you're looking at that solid line, this looks like the normal distribution. In fact, what you'll see is as you sample more and more, this curve gets pushed into that normal distribution. It starts out as kind of a shorter, squattier version of that distribution, a little bit more Rubenesque, but it's essentially the same curve that just has a bit more error correction for those lower sample sizes. So in the same way that I could find my critical values using a normal table, I can find my t-stars or my critical values now using something called a t-table. Let me show you what that looks like. So I've got a t-table here. I'm going to make this side by side so I can see the two things. Great. And in this t-distribution, it gives me a bunch of different degrees of freedom. And in those columns there, these are all of my different confidence levels. So for example, if I had a degree of freedom of 15, I do. I'm going to go to degree of freedom of 15. And if I wanted to be 90% confident, I would go to that 90% confidence column there. And I would see where those things meet up. In this case, I see that they meet my t-star critical value for 15 degrees of freedom was 1.753. Let's try another one. 51 samples, and I want to find t-star for 95%. First thing I need to be careful about, if I have 51 samples, I have a degree of freedom of 50. Now, sometimes my degree of freedom won't show up on the side here. It'll be between two values. Use your best judgment. Take whichever one it's closer to. So in this case, I'm at 50. That is in my table. Great. And 95. Seeing where those meet up, looks like they meet at 2.009. Let's try another one. I'm going to do 99%. 500 samples, so one less for my degree of freedom, 499. And 499, I have 400, I have 1,000, so it's not perfectly in the table. I can either take the value above, the value below, or average them out, but let's see what column I should be in. 99%, so the last one. So somewhere between 2.588 and 2.581. I might just use 2.588 or so. I personally subscribe to the idea that it's a good idea to assume you have less control instead of more control. So I always personally use the smaller of the 2 degrees of freedom that I have options for. But really, these values are so close, you're probably not going to notice the difference. Let's do one more. T star. And if you're following along at home, try pausing the video and see if you can figure out what that degree of freedom is. And then use the table to the best of your ability to see if you can find T star if we're dealing with 99% confidence. Okay, assuming you paused the video and tried that out, let's take a look. One less. So I have 9, 9, 9, 9. I think that's right. I hope you're double checking my work there. 9,999. And I'm going to go to the 99% column. It's between these two values. It's really, really large. So maybe I take that larger value, 2.576. And oh shoot, I'm getting a little bit of deja vu. 99%, 2.576. I think I've seen that before. Let's look at some of these other values to see if those are familiar. 95%, 1.96. That's my critical value, my Z stars. I used to have 90 go to 1.645. 95% was 1.96. And 99% went to 2.576. So actually this last row in your table, if you're dealing with a really large N, then your T-scores become Z-scores. I'm seeing that in the graph as well. So if I sample more and more and more, these dotted lines are a T distribution. The solid line is a Z-score or a normal distribution. Okay, taking inventory, a lot going on. My formula for my confidence interval is X bar plus or minus T star, S over the square root of N. X bar and S so I can get in my calculator. T star I'm getting from a table. So let's try to put all this together, and we're going to do 2 confidence intervals super fast just to see what this looks like from start to finish. So my formula is going to be my center plus or minus my T star, whatever my degree of freedom is, S over the square root of N. So suppose I have a sample average of 18 inches. Great, I'm putting in 18. On the side, I'm writing down my units, inches, so that way I don't forget when I write down a conclusion, inches. T star, 31 samples, so my degree of freedom is 1 less, it's 30. My S is 20 over my N is 31. I want to be 90% confident, so I'm going to find the 90 column. Where that meets the 30 gives me 1.697. I'm going to type this into my calculator once with the plus and once with the minus to get a low value and a high value. Let's see what that looks like. So I have 18 minus 1.697. I have 20 over the square root of 31. And when I put this into my calculator, I ended up getting a low value of 11.90 units, inches. Doing the same thing with the plus instead, I end up getting 24.10 units, inches. So my sentence that would go along with this, we did it together. We are 90% confident that the interval of 11.90 to 24.10 inches contains the true population average. So now I'm able to do these intervals and write conclusions about averages instead of just percentages. That's a huge win because now I can deal with data that is quantitative, things that have units, instead of just dealing with categorical data where I had stuff like yes or no, red or blue. So I'm able to look at a much more deeper subset of statistics. Let's look at another example involving cats. Mr. Wary weighs 100 cats, so my sample size here is 100. So if I have 100 samples, I have a DF of 99. They have an average weight of 8.5 pounds. Well, this is just those 100 cats. This isn't every cat in the world, so this is a sample average. So I have an X bar of 8.5 lbs. A standard deviation also for a sample, so an S. And since I know S, I'm going to use this t distribution. Assuming the sample is representative, okay, so I don't have biases. I have less than 10% of all cats in the world, and 100 is bigger than 30, so my assumptions look good. Create a 95% confidence interval for mu. This would be the average weight of all cats worldwide based off of just these 100. Let's find that critical value for 99 and wants 95%. So I'm going to the 95% column, and 100 is really close to 99. So let's rock this 1.984 value. Okay, just a little bit of scratch work on the side. I'm going to plug these all into my interval. I have X bar plus or minus T star for whatever my degree of freedom is. I have S over the square root of N. Average of 8.5. 1.984 is my T star. My S is 1.8. My N is 100. Units, pounds, not a bad idea to write that somewhere just in case I'm afraid of forgetting that. I'm going to type this into my calculator, and I'm just going to type everything after the plus or minus here. I'm breaking it up into small steps, so if you're afraid of making a mistake in your calculator, that's not a bad idea of trying to break it up into smaller pieces. But I'm also doing this to review a little bit of language with you. This is my center of my interval. And just as a quick reminder, everything after the plus or the minus is referred to as the margin of error. So I could already write a sentence out for what's going on for this problem. I am 95% confident that the average weight of cats is 8.5 pounds, give or take 0.357 pounds. Let's go ahead and just use this though to come up with a low value and a high value. So 8.5 minus 0.357. So I have 8.143 lbs. I'm taking that same interval and I'm changing a minus to a plus. I have 8.857 units lbs. Whenever you have an interval, you should write out your sentence. We are 95% confident. I'm going to write ... You should really write out the whole sentence here. Let me finish that sentence. We are 95% confident that the interval of 8.143 to 8.857 pounds contains the true average weight of a house cat. So this is kind of interesting. I'm able to make a conclusion about the entire population, world population, and I only sampled 100. So questions might be, well, how do I know if something is fair or not fair? So if someone said the average weight of cats is actually 9 pounds, I can't believe you thought it was 8.857. I could be like, well, hold up, I should be able to test this, come up with a p-value, and say, I have statistical evidence that you're wrong when you say 9. So let's look at what that process might be for lesson 7, hypothesis test for averages. And I use this table when I'm working with confidence intervals. I don't use this for hypothesis tests, so I'm just going to ignore that for a second. And my second part of this, besides intervals, for mu, I want to test claims. About these population averages. And I have the 4 steps of our hypothesis process on the side here. I state the hypotheses. In this case, I'm dealing with averages, so this is going to look like mu equals some number. Mu is either less, left-tailed, more, right-tailed, or not equal to some number, two-tailed test. My second step is going to be to determine the model and assumptions. Third step is going to be to calculate the p-value. And my fourth step is conclusion. I actually already have the model. My model is a central limit theorem which says that x bar follows a t distribution with some degree of freedom, average of mu, and standard deviation of s over the square root of n. If I know s, I use t. If I know sigma, I would use z-scores instead. Assuming it's random, assuming independence, back up for that is the 10% rule. And assuming I have a large sample, large in this case meaning 30 or more, or it starts normal. I mentioned that t-scores were like z-scores and we saw the curve. I want to be really explicit by what I mean by that. I used to find z-scores by doing value minus center over standard deviation. Well, now in order to find a t-score, I'm going to take value minus center, and I'm going to divide it by standard deviation. It's the same formula. When I'm talking about value, this is my sample average, or whatever my sample data is. When I'm talking about the center, this is going to be the value that's being claimed. And my standard deviation is going to be whatever the standard deviation is from my model. I'm going to be looking up t-scores using technology here today. But this will be the process for doing it. I'm going to state the hypotheses. It's going to involve mu. Second stage is going to be to use this model that I got going on here. Third stage is going to be to calculate my t-score using this general setup, and then looking it up to get my p-value. And then my fourth step is conclusion. The way that the conclusion has been working so far is if your p-value is smaller than your alpha, if your p-value is low, then your null must go. If you have a large p-value, that's when you fail to reject a null hypothesis. Let's just do it. 4-step process. Example 1, it is claimed that Tylenol lasts for 4 hours on average after a clinical study involving 30 randomly sampled patients. Mr. Ware is led to believe that the average is actually less than claimed. This data yields an average of 3.25 hours with a standard deviation of 1 hour. Test the claim. Okay. This is a claim about averages. So it is claimed that the population average is 4 hours. I think the actual average is less. So same symbol, same number, different inequality, testing less. Reminder, your alternative hypothesis will tell you which way you're going to be shading. So if I'm looking at numbers less than whatever my value is, this is going to be shaded to a left or left-tailed test. My model, x bar is going to follow a t distribution with some degree of freedom, mu, and then I have s over the square root of n. Reading through this again, clinical study involving 30 randomly sampled patients. So I have 30 is my N. My DF is one less, so my DF is 29. Whatever number I have for my null hypothesis, I'm going to assume it's true. I've said every time mu shows up, it's 4, so I'm going to be putting 4 in for my center. S is my sample standard deviation of 1. And N, I'm looking at 30 samples. If you'll notice, I've not touched this 3.25 hours that I got from my sample, and that's because that is an X bar number. My formula right now, this X bar that I have here, this is the name of the model. It says I will be eventually using that 3.25, but not yet. I think that average should be close to 4, though, give or take whatever the standard deviation is. So let's type that SD into our calculator. I get 0.183-ish or so. Assumption check. Random. Says randomly selected patients. So says random. Whenever I see a study says they did a random sample, I'm usually super suspicious about that, though. It's remarkably hard to create something that doesn't have any bias. So if you see that, I would actually follow that up and try to figure out where that information came from, just to make sure it's actually fair. Independents are 10%, while one person with Advil should not affect another. So I have independence in my sample. I'm feeling pretty good about that. Large N, 30 or more samples or it starts normal. I have 30. 30 is bigger than or equal to 30, but just yet it's equal. So I pass all 3 of my assumptions. I'm in good shape. So I have my hypotheses. I have my model. I did my assumption check. I'm moving on to this 3rd step, which is p-value. The p-value is the likelihood of the sample data. The sample data, this is the first time that sample average of 3.24 hours is showing up, or more extreme. Whatever symbol you have in the alternative hypothesis, that is getting pulled down into this 3rd step. I'm going to have this thing be shaded to the left. The likelihood of the sample data, or more extreme, if the null hypothesis is true. So assuming the average should have been 4, give or take 0.18 or so, how likely is it that you get an average of 3.25 or less? So the p-value is going to be the size of the shaded end block. It's going to be this little piece here. So let's go ahead and calculate this t-score, and then let's look it up. T is my sample value minus the claim in the center divided by my standard deviation. So p-values always compare your claim and your sample data. So in this case, my value was 3.25 from the data, and the claim was 4. So I'm off by negative 0.75. I don't know if that's off by a lot or a little. That really depends on what I'm counting by. If I'm counting by 0.183, let's figure out how many tick marks away this thing would actually be. So I have negative 0.75 divided by 0.183, and I am negative 4.098 standard deviations away. So just as a bit of a reference here, if this was a z-score and I was 4 standard deviations away for a z-score, this would be considered an unusual value. It would be off my normal table. Now, unfortunately, I don't have a nice T-table based off of every single possible degree of freedom that gives me a grid that I could look up all of these p-values. I would have to have a whole book of those things. I could, in theory, find a book like that, but this is the 21st century. We have technology. Let's use that technology. I'm going to have my TI-83 and 84 and my TI-89 instructions here. There are also tech videos for how to use GeoGebra to do the same stuff. But here's what I'm going to do in my calculator. If I have an 83 and 84, I'm going to hit the second button. I'm going to go into my variables, and I'm going to choose the option for TCDF. When I'm choosing this option for TCDF, it's going to ask me for the lowest value that I have shaded in. This is the leftmost part that is shaded. So whatever the barrier is, left barrier of your shaded part, to your highest t-score, this is the rightmost part of your shaded. So it's pretty much just asking, like, where am I shading stuff in? So where do I put in all this paint? So it needs the low value and the high value to put that in. And then finally, it wants the degree of freedom. Let's look at our picture. So our value when it's the left end of this thing, well, this end just keeps going on forever towards that direction there. So my smallest t-score, I don't really have one. It just keeps going towards negative infinity. If I'm looking at the rightmost t-score, well, it stops right here. The t-score that it stopped at was negative 4.098. I'm going to pause for a second before I do anything else. I want you to notice something. My value might have been 3.25, but this TCDF only knows how to look up t-scores. So that's why I'm using this t-score here instead of that sample average value. Degree of freedom, I have 30 samples. So in this case, I have a degree of freedom of 29. Okay, in my calculator, I'm going second vars. I'm choosing TCDF. I'm typing in my low value. I don't have a negative infinity button on my calculator, so I'm just going to do negative, and then I'm just going to go to town on the 9 button. One note, this is really easy to mix up. There's a negative button and there's a minus button. Make sure you're hitting the negative button when you're doing negative 99999. Otherwise, your calculator is going to give you an error. Likewise, negative 4.098. My degree of freedom is 29. I paste, and I hit enter. If you have a TI-83, when you're doing this step, it's actually going to look a bit more. Give me just 1 second. Perfect. Like this in your calculator. It's just going to start with this TCDF, and it's going to blink with you ready to type in numbers. When this happens, you type in your low value, negative infinity, comma. Your comma is above the 7, negative 4.098, comma, the comma button's above the 7, my degree of freedom 29, and then I hit enter. So I still type in the numbers in the same way. I just have to hit comma in between them if I'm using a TI-84. TI-89, I go into apps. I choose the app for stat list editor. And up at the top, I'm choosing distribution, so F5. And I'm doing the T distribution, TCDF. Low value. Now the 89 actually does have a negative infinity. The infinity shows up right here, so I could do negative and then this diamond button followed by this button with that symbol to get this negative infinity to show up. My upper value was negative 4.098. My degree of freedom was 29. This gives me 0.000153. In my TI-84, it gave me 1.53 E minus 4. Do you notice that, E minus 4? This is in scientific notation. So if your calculator gives you 1.53, and you're thinking, well, 1.53 is 153%, that must be my p-value. Be careful. You have to include the E minus 4 if your calculator gives that to you. You can't have a p-value that's bigger than 1. That represents more than 100%, and that's not possible. So you probably actually have something that's really, really small. Moving the decimal 1, 2, 3, 4 spots over gives me something like this, 0.000153. If your p-value is low, conclusion time, then your null must go. Reject the null hypothesis. If you're rejecting the null hypothesis, this means you have evidence of the alternative. In this case, I have evidence Advil lasts less than 4 hours on average. If I wanted to know how long Advil actually did last, I would want to go back and do that confidence interval. So usually I do these things in practice in the reverse direction than what we just learned them. I usually do my hypothesis test first to determine if something is fair. If it is unfair, then I follow it up with a confidence interval to figure out exactly how it is unfair. Hypothesis tests just answer yes or no, fair or unfair. Confidence intervals give a range of possible values. I want to practice looking things up with your t-scores just a little bit more. T of 2.31 or higher, the degree of freedom is 15, okay. T-scores are the number of tick marks away, so if you're trying to draw a nice picture, this is 2.31 or more tick marks, great. Or more, so it's shaded to the right. This area, TCDF, looks like it starts at 2.31 as a t-score, and it keeps going on forever. The high value here looks like it goes towards positive infinity. So this starts at 2.31, comma, goes to infinity, comma, the degree of freedom already been set up for me is 15. I'm going to type this into my calculator and I'll see what I get. TCDF 2.31, a whole bunch of 9s because I'm doing this on my 84 and it doesn't have an infinity. DF of 15. I get 0.018 or so. Let's look at another one. Negative 1.5. This thing has an equals. That doesn't matter. It can have an equals or not have an equals. It's still going to be the same setup. Or less, though, is the more important part. Shade to the left. This thing keeps going on forever in this direction. That direction points towards negative infinity. And this stops being shaded in here at negative 1.5. So my low value is negative infinity. My upper value is negative 1.5. 31 samples gives me a degree of freedom of 30. TCDF, negative whole bunch of 9s, negative 1.5, and 30. This gives me an area of 0.072%. I'm going to do one more. I'm not going to do 5 or 6. You could do those on your own if you would like, but let's do area between negative 1.96 and positive 1.96. So TCDF degree of freedom is going to be 1 less than 10,000, so 9,999, and I'm shaded between negative 1.96 and 1.96. I'm going to type this into my calculator and see what I get. And I get approximately, 0.95. So if I go up and down 1.96 standard deviations, I have 95% of my area. That's my critical value. That's actually matching up with the result that we had from earlier. I want to do one test from start to finish. This will be the last thing we do for hypothesis tests and confidence intervals for one average in this video. But there are still plenty of other smaller videos with single examples about how to do these topics and also how to use technology to find some of these values. But let's suppose Subway claims that their subs are 12 inches. So first step, they're claiming subs are 12 inches. Local woman tests 100 subs, gets a sample average of 11 inches, a standard deviation of 2 inches, tests the claim that it is less than 12. So I'm told it's 12. I think it's less than 12. My model X bar should follow a t distribution. Mu S over the square root of n. If I have 100 samples, I should have 99 for my degree of freedom. Mu is 12 inches. S is 2. N is 100. I type that into my calculator. Square root of 100 is 10, so I don't know if I even need a calculator. Dividing by 10 just moves the decimal. I have a standard deviation of 0.2. I should also probably check my assumptions, but I'm just going to keep going to my third step, my p-value step. P-value is the likelihood of my sample average of 11 inches, or more extreme. In this case, I'm shaded to the left. I'm testing for less. So if I'm drawing my picture, my center is 12. I'm counting by 0.2. And I'm looking at 11 inches. Whoa, that's way out there. Or less. Now, before I can, for the p-value, do my TCDF low, high, degree of freedom business, I need to make sure I have t-scores. So I'm going to find the t-score for this 11. So t is the value, 11, minus the center, 12, divided by my standard deviation. I do 11 minus 12 divided by 0.2 in my calculator, and I get a t-score of -5. So this thing starts way out at -infinity, and I keep shading until I get a t-score of -5. If I have 100 samples, my degree of freedom is 99. So TCDF negative, I'm just going to do a whole bunch of 9s, to -5. My DF is 99. When I do this, my calculator gives me 1.24. Oh yeah, I got to watch out for that E thing. E minus 6. So this means I move my decimal 6 times over. 1 gets me on the other side of the 1. And then 5 more zeros. 3, 4, 5, 2, 4 is my p-value. This is a really, really small p-value. And if you have a small p-value, you're going to reject the null hypothesis. If you're rejecting the null hypothesis, this must mean that we have evidence that the average length of subs at Subway is less than 12 inches. So if this person was upset at Subway, they said it's 12 inches, they now have statistical evidence that it is in fact less than that. So a follow-up question might be, how much less? And that would be answered using a confidence interval. Our confidence interval would take this average, x bar, and it'd go up and down some number of standard deviation-like things. Let's fill in some blanks and figure out what that interval would actually look like here, because I have these numbers. X bar is 11. T star for, it's 100 samples, so my degree of freedom is actually 99. I'll look that up in a second. My S over the square root of n, this is 2 over the square root of 100. I already know that to be 0.2. I could use that decimal if I prefer. But I'm going to go to my T-table here, and let's create a 90% confidence interval as a follow-up. So 90%, this is really close to 99. I'm going to use a t-score of 1.66 or so. I'm going to type this into my calculator once with the minus. 11 minus 1.66 times 2 over the square root of 100. On the low end, this gives me 10.668 inches. I'm going to do the same thing again, this time with a plus. And this gives me 11.332 inches. So if someone asks me, how long do you think sandwiches actually are at Subway? I would say I'm 90% confident that the average sup length at Subway is between 10.668 inches and 11.332 inches. This result is statistically less than 12 inches. Testing that gave me a p-value of 1.24 times 10 to the negative 6, a really, really small p-value. So that was a look at how to do both confidence intervals and hypothesis tests. That's lesson 6 and lesson 7 that have been combined there. If you'd like to look at these lessons individually, there are videos for both lesson 6 and lesson 7 that goes into a little bit more detail, but I wanted to give you one sort of video that covers all of it at once in case that's what you're looking for.